So today I'm going to talk about the topic, which is the transboundary air pollution and the health impact in China. Okay, so in the photo here that you can find a lot of photo in the cities in the Asia that they are suffering from the air pollution. Especially I like this photo because I remember a few years before when I talk about this topic with this photo, when I say this is the normal situation and the other one is the aerosol. Audience ask me, are you sure that this is normal or this is normal? So this is what we call the new normal right now, that air pollution getting more frequent and more intense. But the question is, how can we understand the science behind and then help the governments to mitigate the air pollution issues in different cities over the world? All right, so first of all, let me briefly introduce my research in the topic. Like here that I have two research directions and interests. The first one is the air quality and climate interactions, and also have an interest to look at the associated impact, go beyond the human health as well as the planetary health. So as shown in this figure that everything would connect to each other, especially that if we have the anthropogenic or the emission from natural process. So that would affect our air quality. But at the same time, climate will also contribute or even enhance the air pollution issue. So how this kind of relationship would affect the air quality and then would eventually impact to our health, human health here is what I actually have the interest. And eventually, I would like to affect the control policies in government to mitigate the problems that I'm interested in here. So let me talk about why I have an interest in air quality. The World Health Organization reports that 9 out of 10 people over the world actually is suffering from the polluted air. So estimation tell us that 7 million people die because of the air pollution in a year. So among the 7 million people, around 4 million premature mortalities is due to the ambient, or you call it an outdoor air pollution issue. So let me show you a very nice figure here. This is my favorite figure here. So this figure showing the annual PM 2.5 concentration in different cities over the world. So here we got like a 2,600 cities here. So as you can see, y-axis is each city here, and x-axis is showing the cities here, and the y-axis is showing the PM 2.5 concentration level. So as you can see, probably you may spot to the highest one, right? So let me tell you, the highest two are actually talking about the cities in India. All right, but if you look at to the top, at the same time, you may probably have an interest to the large patch here. All right, so can you guess what's this? All right, so this is in China. All right, so if you talk about the average over the PM 2.5 concentration from all the cities here, we are talking like the 19 microgram per meter cube. All right, so this is the global average in cities. All right, but if we average the PM 2.5 in the cities in China, we got 48 microgram per meter cube. So as you can see that this is more than double than the overall global average. So that is the problem, especially that, as I mentioned, the health impacts are very remarkable here. So that is the problem that we should address. All right. And then in terms of air quality, all right, just in case some of you may not have a background of air quality, so let me explain. In terms of the air quality, we have basically 3 contributors in general, very general. So the first one is if we walk along the streets, we are maybe suffering from the pollutants from like vehicles next to us. So along the streets, we have a spike here that is representing the roadside air pollution. But if we look at to a one more level up in terms of the spatial scale, we have the concentration contributed by the city emission sources like power generation, industry, etc. So that is kind of the higher contribution would in the city center. Right? So this is why you can see higher in the center and then lower in the boundary of the city. So one more level up in terms of the spatial scale is the regional contribution. So as you can see that the spatial rise that we have a relatively flat contribution because if we have the regional air pollution issues, typically we have a relatively large patch of pollutant transport from one location to another location. So adding them together, we got the air quality in a city. So today, because of the time, I cannot talk everything here. So that's why I focus on the regional level, which is related to the transboundary air pollution today. All right. So in terms of transboundary air pollution in China, all right. So this is a very important global environmental problem. No matter what scale we are talking, right? For example, like in China, some of the studies looking at the transport of the pollutant from China to another like country like US, right? Or the pollutant transport from China to the surrounding country like Japan or South Korea. And even that is not unique in Asia because that could happen in other countries as well. For example, like the transport, the transboundary air pollution between UK and continental Europe that especially France, they have a lot of interaction among that two countries. Singapore's similar because you also have the interaction between Indonesia and Singapore. So that kind of transboundary air pollution is particularly serious in like July, as you can experience in Singapore, right? Down to the lower spatial scale, like Hong Kong as a city, we also have the interaction among the cities within the peripheral delta region in China, which is located in the southern China here, right? So that becomes the problem because for the local air pollution, local government can control their emissions to mitigate the problems. But when we talk about transboundary pollution, we have to collaborate with other governments together, work together to mitigate the air pollution problems. But the point is, if we don't fully understand the characteristics and the contributions of transboundary air pollution, we cannot formulate effective emission control policies to effectively mitigate the problem. So this is why I spend a lot of time on this topic in order to enhance our understanding of the transboundary air pollution. All right, so this is the case. And there are a lot of research questions about the transboundary air pollutions. So in this talk here, I would like to address 5 questions as I show it here. If you have any other questions, we can still discuss, but I will mainly focus on these 5 so that we have a better understanding of the transboundary air pollution. All right, so I'm going to address one by one now. So the first one is the spatial and the temporal and even vertical patterns of the what we call domestic transboundary air pollution. The domestic means the transboundary air pollution within China, right? So here, what I did is I employ a chemical transport model, which I call it as CMAC, right? So CMAC is a widely used air quality model in air quality studies. So I use this model to assess, to understand the characteristic of the transboundary pollution and even quantify the health impact, right? So for some of you with the background of modeling here, that the model is powerful, that take into account like the input from the meteorological model and also the emission data, initial and boundary conditions. So here is an example of the output that we have 5-dimensional data, latitude, longitude, height, and the time, and also species. Species, we are talking like over 140 air pollutant species that output from the model. So that tool gives us a very important information about the air quality. So here demonstrate the surface PM 2.5 in a year over China. This is ozone. So this is vertical profile in different regions in China. All right, so get to the study here. In order to understand the transboundary pollution among the regions here, so I define the 7 regions in China. and understand their interaction between each other. So as you can see in this figure, we got the northwest China, right, southwest, and northeast, and east China, and also south central, and also Taiwan is included. All right, and here this is the results that you can find. This is the outflow of the pollutant, all right, from the target region shown in the x-axis, right, below the planetary boundary layer and above the PBL here, all right. So there are a lot of information here, so that's why let's focus on the East China, all right. So you can see that for within the PBL, the outflow means the contribution of the pollutant from East China to other regions. All right, so you can see that basically you can find this is 4 regions that the East China contribute. The PM 2.5. All right, the major receiver will be the South Central. All right, as you can see, and some of the portion of the PM from the East China will be transported to northeast, or some of them to Taiwan. This is what the situation within the PBL. But when we talk about the above PBL, you can find the contribution from the East China to the South Central will be relatively lower compared with the contribution in other receivers here. So that is the situation above the PBL. All right. So that the reason behind that is because this is really have a lot of intensive interaction within the PBL between the East China and South Central here. So that is why the contribution is so high here. But if we look at to the inflow means the contribution from other region to East China here. And you can find the major contributor will be the North China and the South Central China contribute to the East here, below the PBL. But if we look at you above the PBL, you can find something very interesting is you can find the Southwest and Northwest outstand compared with the situation below PBL. So this is what we call the super regional transport, because this transport cannot happen in the lower level because topography and other land covers features would block the transport of the pollutant. But when we talk about the above the PBL, this kind of transport will be more effective and can sometimes last for longer because the upper level, they have a less the chance to have the rainfall there. And then because this transport is cross one region, so this is why this is what we call it as super regional transport of the pollutant. All right. So given this kind of the analysis, we can understand the spatial and the vertical, even the temporal characteristics of the transboundary pollution in China. And what we find in terms of the PM 2.5, the contribution of the transboundary pollution can contribute 1/3 to 1/4, all right, of the PM from the transboundary air pollution. So this amount is so huge because that gives the local government to understand that they cannot just mitigate the air pollution by their region itself, but they have to collaborate with other regions to mitigate the 1/3 of the PM 2.5 in their region. The next question is, now previously we talked about like long-term interaction. So how about the situation given like a weather or climate events? So how this kind of events would impact on the transboundary air pollution? So let me show you some of the very interesting cases in Hong Kong, or features in Hong Kong in summertime, particularly, that we sometimes would have the pollutant episode events for a relatively short time, like 1 day or even 2 days. All right. So this is the one episode demonstrated in this figure. So this figure showing the time series of the PM 2.5 in one of the stations in Hong Kong. And you can find this is in the situation in the 2015 August. And then you can find the PM 2.5 jump suddenly, and then drop, and then jump again. All right. So this is very important because that At the same time, we in summertime, sometimes they will associate with the hot events. So this is a problem that this is what I define as hot and polluted episode, HPE, which is defined as an episode with the concurrent high air pollutant concentration level and the ambient temperature. So why I have an interest in this kind of event, because that would give us a serious the health impact, because the high temperature combined with the air pollution effect on our body will be different when we compare with just the solo impact from air pollution to the health, or solo the high temperature to the body alone, right? So this is why the combined effect could be one of the interesting topic in the epidemiological studies. So for this kind of episode with like HPE, as I mentioned, they are always associated with like a tropical cyclone here, as you can see, typhoon, right? And this one is also related to the typhoon around this particular area. So let me give you the spatial, the geographical location. So here is Hong Kong, right? So here is Taiwan, all right? And here is Japan, and here is South Korea. So this kind of the typhoon system would give us this kind of the situation. So now the problem is why and how. So can we understand that? So this is what I did, all right? So in order to answer the questions, I developed an integrated statistical scheme with the non-negative matrix factorization techniques combined with like the backward trajectory modeling, and as well as the concentration weighted the trajectory analysis together to apportion the contribution from the different emission sources to different pollutants in different stations in Hong Kong. All right, so let me give an example. Like here, so this is a sample of the apportionment for the PM PM10, right? Different color represent the emission sources, and then here each column here represents different stations over Hong Kong here, which we have 14 stations covering different locations in Hong Kong. So before we do the analysis, I compare this result with my chemical transport model, and then you can see CMAC, right? So you can see that they are really competitive with each other. So confirm the robustness of the statistical schemes that I developed in this study. So with this apportionment, so next now then I apply that results and the method in the different tropical cyclone event from 2002 to 2012. All right, so among which we have 44 cases with the typhoon signal. All right, typhoon signal number 1, which means if we have a typhoon that is at the location starting to enter the 800 kilometer away from Hong Kong, we will have typhoon signal 1 issue. All right, so for TC3 here is talking about if the wind speed increased to 41 to 62 kilogram per hour, that would increase the signal 3, and the even higher wind speed, higher than like 63 kilogram per hour, we have a signal 8 here. And NTC here means no typhoon signal, and PTC means here is post typhoon signal, means after like a signal 8, for example, right? So here is the total concentration level for different pollutants. As you can see, for the normal situation without tropical cyclone, we got around 50 for the NO2 here, all right? But if we have TC1 happen here, that you can find the pollutant, especially the PM, would increase, right? Will be higher compared with the normal situation. But if we move to TC3, TC8 here, our concentration level would decrease substantially and then get back to the normal situation after the tropical cycle. So now case is, how can we explain that variation here? All right. So first of all, for the TC1 here, we apportion the contribution from local, as you can see in this column here, and then the transboundary pollution in this column here. And then you can find in TC1 that especially in local situation, the differences is not huge compared with normal situation because the emission, no matter what happened, they would emit pollutants, right? So the contribution from the local is pretty stable. But when we talk about the transboundary pollution, you can find the contribution would increase substantially compared with the normal situation. All right. And then at the same time, if we move to the TC3, it drops, especially for the transboundary pollution because of the associated rainfall amounts as well as the stronger wind that can help to disperse the pollutants from the city. So the pollutant cannot be accumulated at that situation. And same in TC8 here. All right. So this is why the contribution from the transboundary pollutions would drop in TC3 or TC8 or after tropical cyclone. So now case is we have interest for the TC1. How come in TC1 the pollutant would be so high, especially from the transboundary pollution? And then I analyzed the meteorological data from the upper air sounding, all right, which is a measurement that the Hong Kong Observatory, they release the balloon 2 times a day and then collect the meteorological parameters at different heights above the atmosphere here. And then you can find in terms of wind speed, and I compare between TC1 means the tropical cyclone signal 1 and the low typhoon signal situation. And then we can find the ground level, they didn't change too much, but in that particular level, starting from that one, 950 hectopascal, the wind speed increased substantially, all the way up to 300 hectopascal here, all right? And then if we look at the north and the northeasterly wind frequency, we can find in TC1, this kind of the northerly or northeasterly wind is more dominant, all right, in the upper level. All right, so this is very important because northerly, a stronger northerly or northeasterly wind would help us to bring the pollutants from mainland China to Hong Kong because Hong Kong is located at the most southern part of China. All right, any associated like northerly wind or westerly wind would bring the pollutant from mainland China to Hong Kong. So this kind of the wind direction is really favorable to the transboundary pollution, especially from the higher wind speed would help us to bring more further upstream pollutant to Hong Kong here. And then if we look at the average, the relative humidity, we can find the air in the upper level is relatively drier than the normal situation. So that would also favorable for the long-range transport because the wet deposition would not be effective to remove the pollutant through the transport pathway. So that is the situation that we find out. And then in order to further understand the situation in like HPE cases, I established one system, the Doppler system, to measure the real-time theoretical profile of the wind and also the aerosol backscatter data in different locations in Hong Kong, as you can see. Now we have 3 stations here. I call this system as 3 dreams because I like dream, this word, and I combine this kind of the first letter in each word that combine these 3 dreams here in Hong Kong. So with these 3 dreams that I observed that during the HPE, we always have the high chances to have like northerly wind as I showed. We see it in the upper air Simon data. And then that is a very important evidence showing that the transboundary pollution in the upper level is one of the important contributor for the sudden increase of the pollutant in HPE. At the same time, something very interesting that I observed is the westerly wind, as I mentioned, that can bring also pollutant from the major cities within the Peripheral Delta region, all right, to Hong Kong. So this kind of high frequency of the westerly wind in different locations in Hong Kong at the ground, near to the ground level will also effectively bring pollutants from other regions or other cities to Hong Kong. So these 2 figures showing the aerosol backscatter from ground level all the way to 2 kilometers above ground, and then you can see a layer of the pollutant at the ground level. So this is the situation in the HPE hot and polluted episodes. So when I conclude different our different studies, and then this is a mechanism that we can summarize. So first of all, this is the map of prairie delta region in China. So here is Hong Kong, all right, and then this is the low pressure system, which is representing the typhoon situation. And then once we have such kind of low pressure system, we have air rise at the center of the typhoon, and then they transport to the surrounding area, and then they have the sinking motion in the surrounding area, for example, like Hong Kong. As I mentioned, if you still remember, I mentioned when the typhoon is around 800 kilometers away from Hong Kong, so this is the location. That is very important for this kind of the high pressure system development, because if the tropical cyclone is too close to Hong Kong, so the associated high wind will remove the pollutant effectively already. So that's why there must be some distance between the typhoon and Hong Kong here. Because of the high pressure system here, the air will sink and suppress to the ground level. That will be favorable for the air pollution accumulation, and also associated with the relatively weak surface wind. That will not be favorable for the pollutant dispersion. At the same time, like what our study found out, that is there is an effective transboundary pollution pathway at the upper level that bring pollutant from other region to Hong Kong, above Hong Kong, and then that sinking motion, as you can see here, will bring the pollutant down to the city. And then so that is reason why the transboundary pollution contribution would drop during that kind of situation, as you can see in the figures before. So this mechanism is very important, especially during the HPE events. And now next question is, how about the situation in El Nino or La Nina winter? All right. So as you can see that I also apply the statistical scheme that to apportion the contribution from local and transboundary air pollution (TAP) here in different ENSO event winter events, right? So the middle one here is talk about the neutral winter, and the left-hand side is the severe La Nina events. So this is the middle part, and this is the severe El Nino. This is a very severe El Nino events. So you can see in terms of the total concentration level for like PM10, PM2.5, SO2, and NO2, you can see in general at the left-hand side, La Nina winter will have relatively higher concentration level. All right, but at the right-hand side, you can see El Nino events, this pollutant level is relatively lower. All right, so now let's explain why they would have this kind of differences. So we apportion the contribution from local and transboundary pollution. In terms of local, they didn't change too much, all right? But at the TAP, you can find the transboundary pollution contribution in the La Nina is relatively higher than normal. And at the same time, for the El Nino winter, we got a relatively lower contribution from the transboundary pollution. But question is why, right? So here we analyze the vertical profile of the meteorological parameters, and then find out that in the La Nina event, winter, we got a relatively lower rainfall amount compared with the neutral winter. But at the same time, for the El Nino winter, we got a higher amount of rainfall. So this is very important because that will enhance the wet deposition of the pollutant. That will not be favorable for the pollutant accumulation. So let's talk about like wind direction. So here is the northerly and northeasterly wind frequency from ground level all the way to the upper level, right? So different color represent different ENSO events. So green color is a neutral, right, compared with a normal situation. And the orange and the purple color represent the El Nino, and the red and blue represent the La Nina. So you can find in the La Nina events like blue and red color, we have more higher frequency of the northerly and also the low easterly wind, especially in the near the ground level here. So that will be important for the transboundary pollution. If you look at the right-hand side here, you can find that the wind speed from the ground level all the way to upper level, you can find that the wind speed, especially at the ground level, is relatively weaker than normal, right? Because this is the comparison between the wind speed between the ENSO event and the normal situation. In terms of wind speed, especially near the ground level, is weaker, while in the El Nino winter, the wind speed at the ground level is stronger. This is very important because wind speed at the ground level would help us to disperse air pollutant. But in the La Nina winter, that we find that rainfall amount is lower combined with the weaker wind at the ground level and the higher frequency of the north and northeasterly wind. So this is a good combination to enhance the transboundary pollution from mainland China to Hong Kong. So that is the explanations of this kind of the phenomenon. For the El Nino, it's just the opposite. This reason that have a higher rainfall amount, lower north and northeasterly wind, and stronger wind at the ground level, dispersing the air pollutant at the ground level. All right. So now next question is, so how about the aerosol feedbacks on the wind and climate? Because we have a lot of the air pollution episode, but we have understanding of how weather and climate impact on the aerosol. How about reversing, right? So how aerosol feedback to the climate and weather? This is what we would like to answer here, right? So this is the figure that showing the interaction between pollutants or even greenhouse gases to the meteorological parameters and then feedback to the aerosol, for example, right? So here we can find that aerosols could have the impact to the radiation through what we call that as aerosol radiation interaction, ARI here. And at the same time, aerosol can affect the weather through the interactions among aerosol and the cloud. This is what we call ACI here. All right, so we could have two pathways that can both together to affect the weather and then feedback to the aerosol here. And this is what I mentioned that if we have the aerosol in the atmosphere, so they can block the solar radiation, reflect back to the space. So that's why the amount of the the radiation reaching to the ground will be reduced. So this is what we call ARI, right? But at the same time, this kind of the interactions would affect the cloud formation. So through this is what we call the ACI, as I mentioned in the previous slide. So this kind of phenomena are very important, especially in the pollution events. So what I did in this topic here is I would like to understand the effect of the aerosol on the deep convection here, because this is very important. If we have aerosol, have the impact on the weather and then feedback to the air pollution. So this is a loop, eventually will further worsen the air quality in the region. At the same time, I would like to understand the effect of aerosols on the extreme rainfall events. So this is very important, especially from the flooding management point of view. Extreme rainfall events will be a very important topic, but how aerosol impact to this kind of extreme events is one of the interests in this study here. So what I did is I applied the weather research and forecast model with the chemistry. So this is what we call WRF-Chem. So this is the schematic diagram of the flow, how the WRF-Chem work with the meteorological part and also the chemistry part here, right? So what I did is I revised the model to include the absorption effect of aerosol, for example, like organic carbon, because previously past research will focus on the scattering effect of aerosol, but very limited number of studies will focus on the absorption effect of the aerosol. Means, like for example, like black carbon, they can absorb the solar radiation warmer the mid-atmosphere, but this kind of phenomenon is not well understood in the previous study. So that's why I revised the model to include the this absorption effect, especially organic carbon. So this is very important. And then right bottom corner here is showing the comparison between the observations as well as the our model results in terms of rainfall amount, for example. Because we talk about the rainfall events. So intensive validation has been done during the study. All right. So what we find here, you can find that very interesting finding is we found that aerosol in the atmosphere would block the solar radiation through the ARI, as I mentioned, right, and also ACI, and eventually would have less solar radiation reaching to the ground level, right? So cooler surface. So that would make our PPL mixing weaker, right? Because the cooler surface. So the PPL is relatively lower than normal. So eventually feed back to the air pollutant because the lower PPL can accumulate pollutant more effectively. All right. And at the same time, very interesting is because of the weaker vertical motion, the convection. So this is why we do not, we have less water vapor transport from ground level to the upper level. So the upper level would be relatively drier than normal. And the lower level, we have relatively higher relative humidity. It's not because more water vapor, it's because the temperature is cooler. Combined together, we have a relatively higher relatively humidity. So this, what we concluded here is with the aerosol in the mid-atmosphere, that would compress the deep convection in the atmosphere. So that is very important understanding because when we do the simulations, especially the future forecast, deep convection is very important for the deep convective cloud simulations. All right. So as you can find it in this figure here showing the x-axis is the vertical velocity and the y-axis is the pressure level. So you can see that the vertical velocity is suppressed. So this is why we have less vertical motion than normal. So that would make the situation, the cloud formation in the middle or upper the troposphere to become less than normal if we have the aerosol in the atmosphere like that. And the other one is very interesting is I found that the aerosol cloud interactions would enhance the precipitation in the extreme rainfall event that I just mentioned. All right, and how can they enhance the precipitation? Is for the local contribution, the local contributed aerosol, they mainly near the ground level, they will enhance the warm rain in the region. So first of all, we have the aerosol from the local emission at the ground level. So this kind of pollutant, the aerosol can serve as a CCM in the atmosphere. And then the cloud drop can be formed attached over the surface of this kind of aerosol. All right, so that would become like what you can see in the figure that the cloud droplet number concentration increase because we would tend to have more smaller cloud droplets in the air. So that would suppress the rainfall, right? Because the cloud cannot be too big, right? But the situation is when the time goes, the rain start. We move part of the aerosol, and then now far fewer aerosol stayed in the atmosphere. Eventually, larger cloud is formed, so that would enhance the warm rain amount from the local contribution, right? But for the remote aerosol transport from other location to the city here, that we find that they are most likely happen in the upper level, as we learned in previous study. And then this kind of pollutant can enhance the cold rain process at the upper level there. So the aerosol transport from another location in the upper atmosphere can serve as a CCM at the upper level, like you can see on the right-hand side here. The supercooling water can condense over the surface of the aerosol. So eventually that will enhance the cold rain process and then would make the cold rain more than normal. As what we found that is the contributions can more than twice of the precipitation increase compared with the warm rain enhancement. So this is very important because that would increase overall rainfall amount, both from warm rain and the cold rain, and also change the rainfall range within the South China, the Guangdong province here. All right? And the last two questions I would like to answer is how the transboundary air pollution form and change during the time, right? So very interesting topic is it the pollutant formed locally, formed remotely, and then transport directly to local, or the pollutant precursor directly transport to local and then form pollutant locally? So this is the questions we always would like to answer, especially for the secondary pollutant like ozone here, right? And what are the interaction among the cities within the Pyramid Delta region in China here? So what I did is I performed atmospheric chemistry model, all right, to understand this kind of interaction. But for your reference, for this kind of study, other studies traditionally use the traditional chemical transport models like CMAC to calculate the relationship between emission to concentration level. Means if I understand the current emission, what is the amount of concentration resulted from the transportation, like the chemical reaction, etc. So this is the traditional chemical transport model. But this kind of model may not be fully representing or simulating the real situation for the secondary pollutant, because ozone, they always undergo the non-linear atmospheric chemistry in the atmosphere. So if we just simply use one baseline case and the one scenario case and then subtract to each other, this kind of method, what we call as zero-on method, may be limited by the non-linear atmospheric chemistry, so cannot be fully represent the real situation. So what I did is I focused on the sensitivity instead of the absolute concentration level. What does it mean? So let me explain. So this is the Gaussian equation. We typically resolve it in our chemical reaction model, and then C represent the concentration level. So different term here represent different process in the atmosphere. So the first term here is talking about the horizontal abrasion. So second term is a vertical abrasion, and then also diffusion, and then this is a reaction, and this is emission sources. So what we found out is I would like to understand the sensitivity. Means if I perturb a certain amount of emission, how the pollutant will perturb accordingly, right? So this is why we change from the absolute concentration to the perturbation, right? So you can see a perturbation of emission. For easier understanding is, let's change this equation to the operator form. And so you can see alpha here is the input parameter, could be meteorological factor, wet deposition, or chemical reaction, or emission, all right? So C is the concentration, and L here is the operator here, the Jacobian of the model operator. So what we would like to know that is, I applied the adjoint, the technologies to this equation to calculate the delta ozone over delta precursor emission, for example, like nitrogen oxides. All right, so let me further explain a little bit more. Here is the figure showing the relationship between emission and the concentration level. So for the transitional study, we're given the baseline emission. I can calculate the corresponding concentration resulted by like different kind of atmospheric process. And we just know one point only. But what we did here is try to understand the tangent of this curve to understand the sensitivity of the ozone with respect to the precursor emission like NOx. So with this sensitivity, we can understand the relationship very clearly, spatially and temporally. That will be very important for the atmospheric science research and also important for the policy formulation. So for my work, that I collaborate with the USEPA to develop CMAC adjoint sensitivity model to simulate the source and receptor relationship of ozone within the perfect delta region in China. So this is Hong Kong. Yeah. All right, and we identified the dominant inferential pathways of the ozone formation. For example, like what I mentioned, I identified some of the grid that they contribute to the situation that the ozone can form remotely and then directly transport to the local area. And some of the grid or area, they are more favorable for the transport of the ozone precursor and then form locally through the atmospheric chemistry to form ozone in the local area. So we identify this kind of pathways in the study. And one thing very important that we found out that is around 50% of the ozone-induced premature mortality is from the transboundary ozone. So that highlights the transboundary nature of the ozone problem within this, these cities in the perfect delta region here. And then we also quantify the contribution from different locations to the ozone in different cities here. And next one is I did not just apply the sensitivity concept to the ozone, but also apply to the PM 2.5, which is a very important pollutants. And then this time I use forward model, which is called what we call the high degree decoupled model. We look at to the sensitivity of the PM 2.5 with respect to different kind of emissions. As you can see, this is the cities in the perfect delta region. We have 9 + 2 cities. And then here is the result that we found out in January, April, July, and October. They have different portions from different contributor to different cities. All right, let's take it, for example, like Hong Kong, the first column here. The blue color represents the Hong Kong contribution to itself. All right, so relatively smaller in the winter case, but larger in the summer case. That's because in winter case, Hong Kong has the prevailing northerly wind, so more pollutant from the outside to Hong Kong. But in summertime, we have southerly wind, so we don't have too much sources in the southern part of Hong Kong except like shipping. So this is why the portion or contribution from Hong Kong itself will be high. All right. So in this figure here, we can find the intensive interactions of the contributions among the cities in the region. And here is the very interesting result that I would like to share, especially in this talk is we understand the sensitivity of the PM and different species with respect to precursor emissions. For example, like here is the sulfur dioxide. All right. So this is the figure showing the this sensitivity along different VOC NOx ratio. So VOC is volatile organic compound and NOx is nitrogen oxides. So this ratio to some extent represents the background composition. So with the lower VOC NOx ratio means urban because we have relatively less vegetation in Hong Kong, right? And more intensive NOx emissions within the city from light transportation, for example. So this is why low VOC NOx ratio representing the urban area. And for the another end is rural area because we have vegetation, which is a major contributor of VOC in the city, and relatively less traffic, so NOx relatively lower. So this is why a higher VOC NOx ratio represents the rural area. And the different color represent different species means, for example, like the orange color here is the sensitivity of the sulfates with respect to the SO2 emission. Right? So you can see the orange color is always positive. It is because if we emit SO2 emission, sulfate will increase. All right, it's kind of easier to understand. All right, but very interesting is you can find that in the urban setting that this kind of the sensitivity is relatively weaker than the rural area. All right, because in the rural area, the SO2 emission at the concentration level is relatively marginal because we don't have too much source of SO2 in rural area. So this kind of sensitivity is more important in the rural area. But another thing interesting is the red color.
Less than 5 minutes, Steve.
All right.
Yeah.
It's going to finish soon. All right. In the red color here is the nitrate. Very interesting because you can find that the nitrate sensitivity is negative. Means if we increase SO2 emission, nitrate will decrease. Interesting. That is because there is a competition between SO2 and NOx to react with ammonia. And ammonia will have a preference to react with SO2. So this is why if we have more SO2 emission coming in the air, so the SO2 will react with the ammonia, right? So less ammonia available for the NOx reaction. So this is why it would increase sulfate but decrease nitrate. This is very important because for the policymaker, they have to understand if their city is suffering from sulfate or suffering from nitrate, would have totally different strategies to control the emission, especially for the SO2. So this is one of the examples only. We have more interesting interactions that I can share. But here today, because of time limit, I can't share everything. But if you have questions later, we can discuss more. And this is the questions I try to address in this talk here because of time. Hopefully that you have a brief understanding of the very interesting topic, transboundary air pollution, especially in China. And this is the reference. And let me know if you have any questions. Thank you.